Hi everybody, this video is intended for watching before our flipped classroom on 4.9. We are going to work through the problems from the book, page 326 through 327, numbers 3, 4, 5, 7, and 10, and I have them copied down for us in the notes below. So we're going to be working on the Pascal's path problem. Miss Pascal likes to take a different route to work every day. She will quit her job the day she has to repeat a route she has already taken. The grid of streets below shows her home and her workplace. She only travels north and east and never backtracks. How many days will she work at her job? So in the book, they talk about some different ideas of ways to set this up. And one of the problems that they talk about, they say, eventually Mark decides to start from the very beginning. He wants to write on each street intersection the number of different ways Miss Pascal could reach that intersection and copy the diagram and help him fill in at least 10 more spaces. So if here's the home and here's work. If we were going to reach the first space, there's only one way to do that. If you were going to go to this space right here, there's also only one way to do that if you're traveling north and east. It would be just to travel east. There's also only one way to travel one spot north. If we wanted to find the number of ways to reach this circle or this intersection, we could either go to the right one and up one, or we could go up one and over one. So there are actually two different places or two different ways that we could reach that intersection. Similarly, we could fill in some more values on our Pascal's path. So if we just wanted to find the number of ways to reach this circle or this intersection, it would be just to go up. So there would be one way to do that. Similarly, there would be only one way to reach 3 intersections to the right. Now, if we wanted to find, I'm kind of working on diagonals if you can tell, but if we wanted to find the number of ways to reach this intersection, there would only be one way, and it's just to go directly to the right. Similar up here, you just go one way up. Now, to fill in the rest of that diagonal, it gets a little trickier. So we could go, let me get some different colors here. Get some of our lines out of the way. So we could go 3 to the right and 1 up. There's one way. You could go up and to the right. Or you could go to the right, up, and over. So there are 3 different ways that you could reach this spot. You could use similar patterns and also have 3 ways to reach this spot. So these numbers should be seeming very familiar to you. They should be seeming like they're coming from places that we've talked about them before. Okay. Similar ideas for those intersections on the end. And I'll do one more. So if we wanted to find this circle right here, we could go to the right and up. So there's 1, 2, 3, 4. And you could continue to fill in the rest of these items. I would suggest that you work on a few on your own. Maybe pause the video, try a few paths, and then come back to this and see if you're correct. So I would suggest if you haven't paused the video to go ahead and do that. See if you can fill in some of the intersections on your own. Oops, I made a mistake. There we go. So hopefully you tried a few of those paths yourself, but there should be a variety of different ways to reach each of the intersections. All right, take a look at question number 4. So question number 4 says, if Miss Pascal travels only 2 blocks, how many different places might she end up? So we're going to go back to our picture that we have, and we're going to go 2 blocks. And I think I will use some different colors to help us here. So here's an option to go 2 blocks. Here's an option to go 2 blocks. Oops. Silly Mrs. B. I'm circling the wrong things. 2 blocks. 1, 2. Here's 2 blocks. 1, 2 north would be here. And then she also could go east and north and end up here. So the question asks us, if Miss Pascal travels only 2 blocks, how many different places might she end up? Well, she could end up in 3 different locations. Question B says, how many different paths are 2 blocks long? Well, this is slightly different. It's asking you about the same intersections. It's just asking you how many different paths are there to get there. So there's 1 plus 2 plus 1 different paths to get there. So there are 4 different paths to reach that location. Question C says, write down all the different paths that she's able to go. So in order to reach this location, she would go 2 blocks east. So that could be E. If she was going to reach this location, she would go east and north, or she could go north and then east. The last possibility up here, she would go 2 blocks north. All right, question number 5 says, in expanding the square n plus e squared, the monomials en and ne are equal. The paths they describe bring you to the same place on the grid. Do equal monomials in the expression of n plus e to the k always describe paths that lead you to the same place? So the answer to this is yes. So if you were going to take n plus e to any power, and you got different, so let's say you had like e squared n, or you had ne squared, or even ene, those would all take you to the same location on your grid. The total number of the e's will be equal, and the total number of the n's will be equal as well. Question number 7. Expand n plus e to the 4th. How does this relate to Pascal's paths of length 4? So let's start by expanding. So we could get e to the 4th, or e. We could get e cubed n. We could get e squared ne, so e. We could get e squared n squared. E squared. You might be getting these in different orders, and that is totally fine. I'm going to hope that I don't miss any of them. Oops. I meant to write cubed here. Some of you might also be asking yourselves, well, can't we just use the binomial expansion? And yes, you can. We're going to talk about that and the connections to the binomial expansion in the next unit, or in the next section, I should say. And a couple more terms to sneak in here. So hopefully we've got all of them in there. The real question is, how does this relate to Pascal's paths of length 4? So notice that we've got every term there has powers that if you would add up the powers, they would give you a power of 4. And let's choose a different color here. Let's say that you're talking about e cubed n. That says go 3 spots to the right and 1 north. So 3 spots to the right and 1 north. You would end here. If we went, let's look at NEN squared, for example. So north, then east, then north twice. North, then east, then north twice. We would end up here. So you'll notice if you continue to do this, that all of the entries that we just listed out are actually showing up on this diagonal. If you would highlight each of them, you would get each of those numbers or each of those locations on that diagonal. And you'll notice that that is 1, 2, 3, oops. Mrs. B is counting wrong again. 1, 2, 3, 4 spots away from home. 1, 2, 3, 4 spots away from home. You might be starting to see the connection with Pascal's triangle. Question 10a. In how many ways can Miss Pascal reach the intersection 4 blocks north and 3 blocks east from her home? So 4 blocks north and 3 blocks east. Let's find that location first on our grid. 4 blocks north, 1, 2, 3, 4, and I believe it was 3 blocks east. 1, 2, 3. So 4 blocks north and 3 blocks east. So you probably have figured this out, that each of the diagonals is a row in Pascal's triangle. So this is row 0, and then they go on diagonal. So row 1, row 2, row 3, we have row 4 circled right now. We could fill in the rows of Pascal's triangle to help us figure out that green spot that we have highlighted. So 1, 6. Remember that for Pascal's triangle, you're adding the 2 numbers that are diagonally in, when we normally set them up, they're diagonally above. Now they're sort of diagonally below and to the right. So if we wanted that green spot, we'd take 15 plus 20, we would get 35. So there are 35 different ways to reach that location. If you remember the connection with Pascal's triangle, you also will remember that you can get that number using n choose r. So in this case, this diagonal that we're working with is the 7th row of Pascal's triangle, and it is the 0, 1, 2, 3, 4th entry. So 7, choose 4, or you could think of it as 0, 1, 2, 3. So 7, choose 3. These are actually the same number. But if you do 7, choose 4 or 7, choose 3, you also will get 35. (10b) says to expand n plus e to the 7th. And what is the coefficient of the e cubed n to the 4th term? So e cubed n to the 4th, if you do this, you should get a 35 as your coefficient. We talked about, or we will talk about, the connections with binomial theorem, but if you remember binomial theorem, it says that the coefficient out front, if you add the 2 powers together, you'll get 7, choose, and then you can either do 3 for the power on the e, or you can do 7, choose 4 for the power on the n. We've kind of already talked about C, but yes, you will notice that A and B are isomorphic. The mathematical process to find those two solutions, as well as the final solution itself, are the same.